Bridge circuits. Bridge circuits are extensively used for measuring component values such as resistance, inductance, and capacitance. Bridges are also used for measurement of frequency, phase, temperature, etc. A bridge circuit consists of four arms. It may be with capacitance, resistances, or inductances forming a closed circuit. The bridge is excited by a DC source or AC source which is applied to two opposite junctions. A current detector is connected to the other two junctions. The bridge circuits use the comparison measurement methods and operate on null indicator principle. The bridge circuit compares the value of unknown component with that of an accurate known standard component. Here, it's an example of a bridge in which it shows the four arms, the null indicator along with the excitation source. Here they have used the DC. The accuracy of the bridge depends upon the bridge components and not on null indicator. High degree of accuracy can be obtained. The circuit of a bridge circuit is shown. So in this, when no current flows through the null detector, the bridge is said to be balanced. So when will the bridge be balanced? The relationship between the component values of the four arms of the bridge at the balancing is called the balancing condition or the balancing equation. Using this equation, the unknown component value can be calculated. Each of the circuit elements is arranged in one of the bridge arms. When bridge is balanced, zero response is obtained from the null detector. There is a relationship between the values of the elements in the arms given by R1, R4 equals to R2, R3. So we have DC bridges and AC bridges. A DC bridge uses resistances in its arms and the source of current is DC. In AC bridges, the bridge arms have either resistances or capacitances or the inductances. The supply used is alternating. The detector used in AC bridge is a galvanometer or the headphones. In DC bridge, galvanometer can be used. Now, let us see the construction of the AC bridge. As I already told you, an AC bridge in its basic form consists of four arms, a source of excitation and a detector. Each arm consists of an impedance either R, L or C. The bridge is excited by an AC source. The source is an AC supply which supplies AC voltage at the required frequency. And we have to see when the bridge is said to be balanced. The bridge is said to be balanced, as we have already seen, when the null indicator shows a zero deflection. So here the source is an AC voltage at the desired frequency. Z1, Z2, Z3, Z4 are the impedances of the bridge arms as shown in this figure. So at the point of bridge balance, the voltage EBA will be equal to EBC, or EBA is nothing but I1 Z1 is equal to I2 Z2. So we can calculate I1 as V by Z1 plus Z3 and I2 as V2 by Z2 plus Z4. So the complex form bridge balance condition can be given as Z1 Z4 equals to Z2 Z3, that is the balance of the magnitude of the impedances, and the phase balance is given as the phase angle of arm 1 plus phase angle of arm 4 is equal to phase angle of arm 2 plus phase angle of arm 3. So overall, the polar form, the bridge balance condition is Z1, Z4, the phase angles of branch 1 and branch 4 is equal to Z2, Z3 with the phase angles of branch 2 and branch 3. As we have already seen, what are the conditions of the bridge balance? The products of the magnitudes of the impedances of the opposite arms must be equal. We have seen this. Z1, Z4 equals to Z2, Z3. And the next condition is that the sum of the phase angles of the opposite arms must be equal. That is, the phase of branch 1 plus phase of branch 4 must be equal to phase angle of branch 2 plus phase angle of branch 3. The next thing is there are different types of bridges which will be useful in various applications. So here the types of bridges are basically the DC bridge and the AC bridge. The two types of DC bridges are the Wheatstone bridge and the Kelvin bridge. The AC bridges are the Maxwell's bridge, the Hayes bridge, the Shearing bridge, etc. Here, if you see the applications of the various AC bridges, Maxwell's bridge is used for measurement of unknown inductance in terms of known capacitance value. It's an AC bridge. Maxwell's bridge is preferred for inductors with low Q factor. Hayes bridge, it is used for measurement of unknown inductance, but the Hayes bridge is preferred for inductors with high Q coils. Next, the shearing bridge. The shearing bridge is used for the precision measurement of the capacitance. The shearing bridge is used for measuring the insulating properties. And the Wien bridge is used for measurement of unknown frequency. If you come to the DC bridge uses, a Wheatstone bridge is used to find out the unknown resistance values. And if you speak about the Kelvin bridge is used to measure the unknown resistor's value at below 1 ohm. So these are few of the various applications of the bridge. Now let us see in detail the Wheatstone bridge. As I already told you, the Wheatstone bridge is a bridge which is used to measure the unknown resistance value. So this is the circuit diagram of a Wheatstone bridge which has the four resistors R1, R2, R3, R4. R1 and R2 are called as the ratio arms. R3 is the standard arm and R4 is an unknown resistor whose value has to be determined, and E is the DC excitation source. A galvanometer is used as a null indicator. Now, the current through the galvanometer depends on the potential difference between points C and D. The bridge is said to be balanced when the potential difference across the galvanometer is 0 volts, so that there is no current flowing through the galvanometer. The voltage from point C to point A equals the voltage from point D to point A. When the voltage from point C to point B equals the voltage from point D to point B, then there is no current flowing in the null indicator. The bridge is said to be balanced. Hence, the bridge is balanced when I1R1 equals to I2R2. The galvanometer current is 0, then I1 equals to I3, which is equal to E by R1 plus R3, and I2 is equal to I4, which is equal to E by R2 plus R4. Combining all these three equations and simplifying, we obtain R1 by R1 plus R3 equal to R2 by R2 plus R4, from which we can say that R1 R4 equals to R2 R3. This is the bridge balance condition of the Wheatstone bridge. R4 is the unknown resistor whose resistance value can be expressed as Rx is equal to R2 R3 by R1. As we have already seen, resistor R3 is called the standard arm of the bridge. Resistors R1 and R2 are called the ratio arms of the bridge. Now, to find out the Thevenin's equivalent voltage, we can draw the circuit in this way. So, this is the Thevenin's equivalent of the Wheatstone bridge. As we know, E Thevenin's is the Thevenin's voltage across the terminal C and D, and R Thevenin's is the Thevenin's resistance found out in the previous circuit. Now, the Thevenin's equivalent procedure to find out the Thevenin's equivalent, the procedure is to find the equivalent voltage appearing at terminals C and D when the galvanometer is removed from the circuit. The second step involves finding the equivalent resistance looking into terminals C and D. The Thevenin's equivalent circuit, the Thevenin's voltage is found as E across the CD equals to E across AC minus E across AD, which is nothing but I1 R1 minus I2 R2. Here, I1 is equal to the voltage E divided by R1 plus R3, and I2 is equal to E divided by R2 plus R4. Therefore, the voltage across the terminal CD, ECD, is equal to R1 by R1 plus R3 minus R2 by R2 plus R4. The Thevenin's resistance, R Thevenin's, looking into terminals C and D, then becomes R Thevenin's is equal to R1 R3 by R1 plus R3 plus R2 R4 by R2 plus R4. The null detector is connected to the output terminals of the Thevenin's equivalent circuit. The galvanometer current is found to be Ig equals to E Thevenin's by R Thevenin's plus Rg, where Ig is the current to the galvanometer and Rg is its internal resistance. So now we have seen the basic operation of the Wheatstone bridge, the calculation of the unrolled resistance, the Thevenin's equivalent of the circuit. Basically, we have seen what a bridge circuit is. So bridge circuit is one which has 4 arms. If it's a DC bridge, we have the 4 resistors. If it is an AC bridge, we may have a resistor or an inductor or a capacitor. The source of excitation in a DC bridge is a DC source. The source of excitation in an AC bridge is AC source with the null indicator connected across the opposite junctions. In a DC bridge, we use a galvanometer. In AC bridge, the null indicator may be a galvanometer or a headphones. We have seen the types of bridges to be the DC bridge and the AC bridge, and the different types of DC bridges are the Wheatstone bridge, the Kelvin bridge. If we speak about the AC bridges, we have the Shearing bridge, the Hayes bridge, the Maxwell's bridge for different applications where we are using to find out the unknown resistors, the value of unknown inductors, the value of unknown capacitances. Can also find out the insulation resistance. Using Wien bridge, you can also find out the unknown frequency. Now, let us practice a small problem. In this Wheatstone bridge example, as you see, this is an unbalanced Wheatstone bridge. We have to calculate the output voltage across points C and D and the value of resistor R4 required to balance the bridge circuit. So what he says is the bridge is not balanced. We have to find out the voltage across the points C and D. Here, the value of resistor R1 is 80 ohms, R2 120 ohms, R3 480 ohms, R4 160 ohms. We have to measure the voltage across the points C and D. It is excited by a DC source of 100 volts. So this is about the circuit given. So now for the first series arm ACB, VC is given as R2 by R1 plus R2 into Vs. So VC is calculated as we know, R2 is 120 ohms divided by R1 is 80 ohms plus 120 ohms into Vs is nothing but 100 volts. So we get Vc as 60 volts. Now Vd. Vd equals to R4 by R3 plus R4 into Vs. So Vd is equal to, we know R4 as 160 ohms divided by R3 is nothing but 480 ohms plus 160 ohms into, as we have already seen, the supply voltage of 100 volts. We get it as 25 volts. Now Vd is 25 volts. So in the problem, we have been asked to find out the voltage Vout across the points C and D. So Vout equals to Vc minus Vd, which is equal to 60 minus 25, which is equal to 35 volts. So to sum up, a bridge circuit are extensively used for measuring the component values of R, L and C. These bridges are also used for measurement of the frequency, phase and temperature. A bridge circuit consists of the four arms, maybe a capacitance, resistance or impedance, forming a closed circuit with a DC or AC source of excitation. Next, the two opposite junctions are connected by a current detector, and the bridge circuits use the comparison measurement method and operate on the null detector principle. The bridge circuit compares the values of the unknown components with that of an accurately known standard component. The accuracy depends upon the bridge components and not on the null indicator. Hence, high degree of accuracy can be obtained by using bridges for the measurement of the component values. In the bridge circuit, when no current flows through the null detector, which is generally a galvanometer, the bridge is said to be balanced. The relationship between the component values of the four arms of the bridge at the balancing is called as bridge balancing, and the equation is a balancing equation. This equation gives us the value of the unknown component. Each of the circuit elements is arranged in one of the bridges. When the bridge is balanced, that is, when zero response is obtained from the null detector, then it is said to be balanced, the bridge is balanced, and the values of the elements in the arms are given by Z1 by Z2 equals to Z3 by Z4, or Z1 Z4 is equal to Z2 Z3. A DC bridge employs the resistances in its arms and the source of current is DC. In AC bridges, The bridge arms have resistances or capacitances or inductances or the combination. The supply used is the alternating supply. The detector used in AC bridges is either a galvanometer or the headphones, whereas in DC bridges, the galvanometer of diastolic moment can be used. As we have already seen, to sum up, the construction of AC bridge is nothing but impedance at audio frequency or radio frequencies are commonly determined by means of the AC bridges. An AC bridge in its basic form, it consists of the four arms, the source of excitation and the balance detector. Each arm consists of an impedance. The AC bridge is similar to a DC bridge except that the arms are impedances. The bridge is excited by an AC source rather than DC source, and the galvanometer of the DC bridge is replaced by a detector. The balance detectors commonly used for AC bridges are the headphones, the tunable amplifier circuits, or the vibration galvanometers, etc. The source is an AC supply which supplies AC voltages at required frequency. For high frequencies, the electronic oscillators are used as the source. The general form of AC bridge is Z1, Z4 is equal to Z2, Z3. In terms of admittance, we can give it as Y1, Y4 is equal to Y2, Y3. From this equation, we can say that the product of impedances of one pair of opposite terms must be equal to the product of impedances of the other pair of opposite arms. The impedances are complex numbers as we know. If we have magnitude as well as phase angle, then Z1 impedance can be given as Z1 at an angle theta 1, Z2 is equal to Z2 at an angle theta 2, Z3, the complex impedance is equal to Z3 at an angle of theta 3, Z4, the complex number is equal to Z4 at an angle of theta 4, where Z1, Z2, Z3, Z4 are the magnitudes of the impedances of the components connected in the four arms of the bridge, and theta 1, theta 2, theta 3, theta 4 are the phase angles of the four impedances connected in the four arms. Here, as per the bridge balance equation, Z1 at an angle of theta 1, Z4 at an angle of theta 4 must be equal to Z2 at an angle of theta 2 and Z3 at an angle of theta 3. So, equating only the magnitudes, the bridge balance condition is Z1, Z4 is equal to Z2, Z3. The phase angles of arms 1 and 4, theta 1 plus theta 4 must be equal to the phase angles of second and third arms, theta 2 plus theta 3. So, therefore, for the balance of AC bridge, the products of magnitudes of the opposite arms must be equal, and the sum of the phase angles of the opposite arms must be equal. So these are the conditions for a bridge to be balanced. As we have already seen the uses of various bridges, the Maxwell's bridge used to measure the inductance in terms of known capacitance. It is preferred for low Q coils. Hayes bridge is also used to find out the inductance values, coils with high Q values. The shearing bridge for measurement of capacitance. The shearing bridge used to measure the insulating properties. The Wien bridge to measure the unknown frequency, and also the DC bridges, the Wheatstone bridge to find out the unknown resistance value, and the Kelvin bridge to find the unknown resistance value, where a value less than 1 ohm. So these are about the bridge balance conditions, AC bridge, DC bridge. Of course, in DC bridge, only the magnitudes or only the component values are taken. In the AC bridge, along with the magnitudes of the component values, we also should consider the phase angles. Then only the bridge is said to be balanced. So different applications of these bridges are already we have seen. You can also use in oscillators, amplifiers for the bridges to be balanced so that you can get in an oscillator the current frequency and all. So this is about the different bridges in measuring instruments which are variously and compulsorily used in number of circuits. Thank you. So this is about the Wheatstone speech. So as we have already seen, the bridge circuits are extensively used for measuring